Hello everyone, we are from Group 14 and today we will be presenting about the liquefaction system, specifically focusing on the natural gas liquefaction system, also known as methane liquefaction. These are the table of contents we will be presenting today. I will briefly present the methane liquefaction process along with a simplified MATLAB simulation developed to model part of it. Methane liquefaction involves cooling natural gas to around negative 162 degrees Celsius to convert it into liquid form, significantly reducing its volume for easier storage and transport. Although the full process involves complex cryogenic cycles, our focus is on modeling the cooling stage using MATLAB. In the simulation, we define relevant constants and apply heat transfer equations to track how methane temperature changes along a heat exchanger. While the model assumes ideal conditions and does not include real-world factors like pressure loss or phase changes, it provides meaningful insight into thermal behavior and energy transfer in cryogenic systems. This simulation supports learning and analysis of liquefaction system performance using a simplified and accessible computational approach. This project focuses on developing a simulation of the natural gas liquefaction process, specifically methane liquefaction, using MATLAB as a computational platform. Liquefying methane by cooling it to cryogenic temperatures enables efficient storage and transport, especially as liquefied natural gas (LNG). The simulation aims to model this process using fundamental heat transfer and energy balance equations, offering insights into system performance. The key objectives include creating a working MATLAB model of methane cooling within a heat exchanger, designing a simple user interface for input and simulation control, and generating graphical outputs such as temperature versus position plots. The study also explores how varying input parameters affect thermal efficiency and cooling effectiveness. Additionally, the simulation helps identify the limitations of simplified models when compared to real-world liquefaction systems. The natural gas liquefaction system, commonly referred to as methane liquefaction, is a thermodynamic process that converts natural gas, primarily composed of methane, into liquefied natural gas (LNG) by cooling it to approximately negative 162 degrees Celsius. This drastic temperature reduction significantly decreases the volume of the gas, making it more efficient for storage and long-distance transportation. The process involves several key stages, beginning with pre-treatment, which removes impurities such as carbon dioxide (CO2), hydrogen sulfide (H2S), water, and mercury to prevent fizzing and equipment damage. This is followed by multi-stage cooling, utilizing advanced refrigeration cycles such as line, plot, and C3MR systems. These cycles gradually reduce the temperature of the gas before it reaches the liquefaction stage, where methane is cooled below its boiling point, allowing it to change phase from gas to liquid. The liquefied gas is then stored in cryogenic, double-insulated tanks to maintain its low temperature and transported using LNG carriers equipped with cryogenic systems. The operation of this system is governed by several physical principles, including the Joule-Thomson effect, where gas cools upon expansion, as well as the use of various refrigeration cycles such as cascade, plot, and reverse Brayton cycles. Heat exchangers play a vital role in ensuring efficient cooling throughout the process. Ultimately, the phase change of gas to liquid under conditions of high pressure and low temperature is fundamental to the success of the liquefaction system, enabling the safe and efficient global distribution of natural gas.
For our methodology, we divide the work into 4 key parts to ensure the accurate and efficient process design. First, in thermodynamic properties compilations, we identify the main components such as methane, ethane, and propane. We gather the critical properties like temperature, pressure, eccentric factor, and specific heat capacity. These properties are crucial for our phase equilibrium predictions and energy balance calculations. Second, in phase equilibrium modeling, we apply the Penn-Robinson and SRK equation of state to predict the vapor-liquid equilibrium at various temperature and pressure. This helps us to ensure efficient cooling and proper separations of gas components. Third, for the energy balance calculations, we estimate the refrigeration slot at each cooling stage, calculate the heat exchanger duties, and assess compressor power requirement. We also identify the energy recovery opportunities and conduct energy efficiency analysis based on recent literature, including Bassioni and Klein 2023. Finally, in process simulations and modeling, we use the MATLAB Simulink and SimSpace for dynamic simulations. This allows us to analyze the system performance under the different operating conditions, helping to optimize the design and improve the overall reliability of the process. Our coding implementation is structured into several sections to ensure the clarity, flexibility, and reliable result. We begin with the input sections where we define all the requirement variables. These include the thermodynamic data like critical temperature, critical pressure, eccentric factor, and heat capacity for gases such as methane, ethane, and propane. We also set the initial conditions for the temperature, pressure, and compositions, as well as the equipment parameter like compressor efficiency and heat exchanger effectiveness. Input validation is applied to ensure physical accuracy and prevent simulations error. Next is the calculation sections where the core simulations logic is implemented. We use the ideal gas law for initial estimations, apply the Joule-Thomson coefficient for temperature drop predictions during expansion, and perform energy balance calculations to compute cooling loads, heat exchanger duties, and compressor power. Phase equilibrium models are included to predict the gas-liquid behavior accurately. This output section use fprintf command to display the key result, including temperature and pressure at each stages, cooling and compressor power requirement, and overall energy uses. The output are well labeled and precise to support the further analysis. We also have a graphical visualization section where MATLAB plots are used to display temperature and pressure profile, cooling load fluctuations, and compressor power trend. These visualizations help identify bottlenecks and guide performance optimizations. Finally, the user interface sections provide a simple GUI. This interface allows users to easily change input value like temperature, pressure, and composition, and instantly observe how these changes affect the result. It also supports the scenario testing and sensitivity analysis, which is essential for refining system design and improving the reliability.
Moving on to the next part, which is the graphical visualization. There are two things in here, which are the graph of temperature versus pressure and the chart of energy consumption. This graph shows how temperature rises as pressure increases, representing the compression phase in the liquefaction process. It simulates isentropic compression, where the gas heats up due to being compressed from 1 bar to 80 bar. The gas reaches 200 Kelvin at 80 bar, which is still above the liquefaction point of methane, which is 112 Kelvin. This highlights the need for further cooling to reach liquefaction and shows how compression alone is not enough. Next, the chart illustrates the total energy required to cool the gas from 300 Kelvin to 200 Kelvin. It represents the thermal energy removed during the cooling process before liquefaction. It helps to identify energy demanding stages and analyze the system efficiency in reaching the target temperature. Now, I'm going to explain about user interface. Firstly, this simulation uses a command line interface in MATLAB. Right after running the script, the user are prompted to enter initial temperature in Kelvin, initial pressure in bar, and gas compositions. These simulations also include error indicating figure to avoid calculation errors such as temperature must be greater than 0 Kelvin, initial pressure must be greater than 0 bar, and gas compositions must be between 0 and 1. After receiving the input, the simulations would perform the calculations and display the results if there was no error. The results that displayed is the final temperature at the phase of methane, either it was in gas or liquid, and the energy consumptions for liquefations. And finally, the script also generates the graphical output using figure and subplot command. Firstly, it shows a line plot showing the temperature change with pressure and a bar chart showing the energy consumptions during liquefaction process. Next, I'm going to explain about the interface usage. Firstly, you have to open the script file in MATLAB and then run the script using the run button. After you run the script, you have to enter the correct values for all the inputs. And then after the calculations was done, it will show you the graphical visualizations containing the linear graph to show the temperature against pressure and the bar chart that's showing the energy consumptions during the liquefaction process.
A very good day to Dr. Haruna. My name is Carmen Q and I will be presenting the result and conclusion. For the result, our input value for initial temperature is 180 Kelvin, while the initial pressure is 70 bar, and the gas composition of 0.98 mole fraction. After putting our input values, we will get this result, which shows that the temperature versus pressure graph, and at the bottom is the energy consumption chart. To summarize, the MATLAB simulation to model the liquefaction of methane under cryogenic condition was successfully developed. By accepting user-defined inputs for temperature, pressure, and composition, the program calculated for final temperature, phase state, and energy consumption. The simulation results confirm that methane could be liquefied at 54 Kelvin under a pressure drop from 70 bar, which estimated energy consumption of approximately 65.4 kJ per kilogram. The expected thermodynamic behavior of the system was then further supported with graphical output. While the model achieved its primary objective as a learning and analysis tool, it contains several simplifications. These include the assumption of ideal gas behavior and a basic implementation of the Joule-Thomson effect, with no consideration of heat exchanger dynamics, real gas equation, or pressure drops. As for future improvements, integrating real gas models could be taken into consideration, modeling temperature profiles in heat exchanger, taking accountability for latent heat, as well as batch simulation and sensitivity analysis. This enhancement would increase accuracy and practical relevance of the simulation, which expand the model's function for engineering, education, and preliminary process design purposes.
These are the list of preferences we use for this project. That is all from our group. Thank you.